This is October-November paper 22. Let's start with this. So the first question suggests what is a vector quantity and how do you understand or how do you differ this quantity from the scalar quantity? So very simple answer would be that a vector quantity has direction. So vector has direction embedded into its full information. The second part is he says underline all the vector quantities. Now be careful that this 1 mark will be scored if you underline all the accurate answers, but if you underline any inaccurate answers, it will be considered incorrect. So vectors are going to be acceleration, energy, mass, momentum. No. So momentum is also a vector. The formula is mass into velocity. So because of velocity, it becomes a vector itself. Now it says that this is a given question, this is a given situation. This is due north, this is due east. The ship itself is moving towards this direction, but the person is running in this direction. So what does it look like to a person standing on the outside? It will appear that the person has covered a distance in this direction or a displacement in this direction because it's moving in both directions. Anyways, now he says use graphical method or a resultant calculation method. You see, it can done be graphically or it can be done calculation wise. So if you want to do this with calculation, that's going to be very easy. It's going to be done in terms of Pythagoras theorem, right? So we have one vector due north, we have one vector due east. We know their individual values, which is 6.8 and 2.4 meters per second. You are supposed to calculate the resultant by using Pythagoras theorem. So this will be 6.8 square plus 2.4 square with the under root symbol because r is also being squared. So you take the square over there, it becomes the under root. So what do you get after this? The resultant by the calculation method is going to come out as exactly 7.2 meters per second. You can do this. And he's also asking you about the angle in the next part. So the angle of the resultant vector in terms of the north pole or in terms of the north. So this is the angle x he's actually asking about, right? So you can use trigonometric ratios to calculate this angle. And if you replace this east vector or eastward vector in the upper direction over here, then you can find out that this is actually a right angle triangle. This looks like a right angle triangle. Then you can use simple tan x or tan theta or tan x is equal to this 6.8 divided by 2.4. And taking tan inverse over there, x comes out as 70 degrees, exactly 70 degrees, right? So this is by calculation. But if you want to do this graphically, he's given you the choice, then this is how you do it. So also ignore this vector. It might appear a bit tilted, but it's not. It's because of the camera angle while I was taking the picture. So you need to ignore that. Now first, we draw the first vector that is due north, but we need to be careful that it has to be exactly 2.4 centimeters. I've measured or I've taken the scale to be 1 centimeter representing 1 meters per second on paper. So this line is exactly 2.4 centimeters. Okay, so this is 2.4 centimeters, but notice I'm not mentioning centimeters. I'm writing this down as meters per second because the question is in meters per second. It's not in centimeters. Similarly, due east, I've taken this line to be 6.8 centimeters exactly, but I will not write down centimeters. I will write down meter per second. Then notice that this line has to be drawn at an exactly 90-degree angle. So for that, you need to use a protractor. You need to use the D. Place the D over here like this and measure the 90 degrees angle exactly and then draw this. Otherwise, you will have small different answers or differences in answer at the end. So be careful about that. Now then, when you've done this vector, when you've drawn this vector, we understand that it's a matter of resultant or finding the resultant. So you can use head to tail method or you can use the parallelogram method. So head to tail, I can replace this vector over here, or I could have replaced this vector over here like this. You can notice that it would still have given me the same resultant, that is from this starting point to this ending point, which is over here, right? So by head to tail method, it's your choice. You can copy any vector on the other side. It would still give you the same answer. But if you wanted to do the parallelogram method, then you have to copy both vectors. So another vector would have been drawn at this point, which is the copy of this vector, right? And when you've done that, then you can see that from the starting point to the ending point, we have our resultant vector, which is in terms of diagram is represented by a double arrow. You can see that there is a double arrow. We have a single arrow for the question vectors. When you've done that, you can measure its length with the meter rule or with the scale or the ruler that you have. You measure its length and you find out that this is exactly 7.2 centimeters. Now, 7.2 centimeters means that according to this scale, this is not 7.2 centimeters, this is actually 7.2 meters per second. So we have our resultant velocity, which is 7.2 meters per second. You don't need to write down the unit, but force of habit, I'm writing this down over here. The second thing is the angle from due north. So this is the angle he is actually interested in. So our angle by calculation comes out as 70 degrees as found before. But since I'm doing the graphical method, I've used the protractor and be able to find this angle to be 71, slightly more than what is being found by calculation. And the next angle can be found by subtracting with 90, because the total angle is 90. But you don't need this angle. I'm just writing this down for your understanding. Okay, the true answer is actually 71. The 7.2 at an angle of 71 degrees, you will see that since he has allowed you to use a graphical method, he will give you a range of answers in the marking scheme. He's not going to be very strict about the diagram. He's going to give some leverage. You will see that the resultant is actually between, I think, 6.8 to 7.2, something like this. And the angle also is between 68 up to 72, I think. So there's always going to be a range of answers. Okay, so if your answer is within the range, it will be accepted. Question number 2. He says that an aircraft has 300 kilograms moving at a speed of 8,000. Calculate the momentum. So momentum is simple formula, that is mass into velocity. So this is 300 kilograms multiplied by 8,000 meters per second. The answer comes out as 2.4 into 10 raised to power 6 kg meters per second. Another alternate unit for momentum is Newton seconds, right? So 2.4 into 10 raised to power 6. The fuel on the spacecraft explodes and the spacecraft splits into two parts. The direction of the parts are moving does not change, which means that if the spacecraft was like this, let's say that they are two parts, there has been a small explosion, let's say at this point, but they're still moving in the same direction. So they are separated, but they're still moving in the same direction. That likely tells you the direction of velocity that they're still moving in. He says that the front part increases its speed to 9,000. So previously when it was moving at a single part or as a single part, it was moving at 8,000. So from 8,000 meters per second, its speed has increased to 9,000 meters per second, but in the same direction. So he's asking you, calculate the speed of the rear part after the explosion. So momentum is conserved under all circumstances. So whatever the momentum before collision should be equal to the momentum after the collision. We know the second part mass is 150. So this is actually 150. This is also 150, but what is its velocity? We know that the final velocity is 9,000 of the first part, but the second part of the part at the back, we don't know that yet. So let's find out. So momentum before collision should be equal to momentum after collision. What's the momentum before collision or explosion? That is the total momentum that you found in the previous part. So this is going to be, it possesses a momentum of 2.4 power 6, should be equal to the momentum after the explosion. So momentum of front part and the back part added together. So mass of the front part into velocity of the current velocity of the front part, which is 9,000 today, plus 150, the mass of the back part, and this is the front, multiplied by its velocity. Should I add plus or minus? I will be adding a plus sign over here. Why? Because it is still moving in the same direction. It's not moving backwards, which means that if it had moved backwards, then I would have put a negative sign. So when you calculate this, make sure that this is actually in algebra. You have to take this over there, subtract it from this number, and then divide the resulting answer with 150. Your velocity answer for the back part is going to come out exactly as 7,000 meters per second. So this can become 7,000, which means that previously, when both parts were moving collectively as a single entity, they had a speed of 8,000 meters per second. Now, after the split, the forward part is moving at a speed of 9,000 meters per second, and the back part is moving at a speed of 7,000 meters per second, all albeit at the mass of 150 kg. Collectively, previously, they were moving at 300 kg. They had a mass of 300 kg, right? So this is before, and that is the after situation. The total kinetic energy of the two parts after the collision is greater than the original kinetic energy, and most definitely the explosion does add energy into the system. It does not take it away. So he says, what is the energy transfer? So we know that the final product is kinetic energy. Where is this energy coming from? Now, since it is because of the fuel or ignited fuel, so we can say that it is actually coming from the chemical potential energy converting to kinetic energy of the system after the explosion. We know that petrol, fuel, wood, plastic, upon burning and combustion, they release chemical potential energy converted to other forms. The explosion lasts for 0.2 seconds. He says the average force on the front part. So we are only going to focus on the front part of the system. What has changed for the front part of the system? So again, let me draw this situation again. This was the back part. This was the front part. They collectively have a mass of 300 kilograms and they are moving at a speed of 8,000 meters per second. This is what was the initial situation. The current situation was that the front part is now, because of the explosion, moving at 9,000 meters per second and has a mass of 150 kilograms, right? Okay. So what has changed for the front part? What is changing for it? Now, for the force, we understand that force is equal to change in momentum divided by change in time. We have the change in time, that is 0.2, but we don't know the change in momentum. So for that, we have to be a bit clever. So what is, for the change, we can say that the final momentum minus initial momentum divided by time taken for the process. What's the initial momentum? So 150 kg was moving at 8,000. And what's the final momentum? So 150 kg was now moving at 9,000. So 9,000 meters per second at 150 kg minus, because of the formula, because this delta in English simply means change, and change means a minus sign in the formula. The initial situation was 150 only for the front part at a speed of 8,000 meters per second. All of this happened in a time frame of 0.2 seconds, which is the value of t. So to bring about this change from this situation to this situation, or from this situation to this situation, in a time of 0.2 seconds, how much force would need to be exerted to do this job? So the force comes out as 7.5 into 10 raised to power 5 newtons when you solve this correctly. Question number 3 suggests a question from the center of mass and lamina, right? So we have an irregular shaped lamina, 50 gram mass, and it's being held in a small hole H, the edge of the lamina. And then he says that G is the center of gravity. So in terms of G, there will be a vector downwards in terms of W. And H is where it is being held from. So H will be the pivot of the system. If you want to look at this from a convenient perspective, from a beam balance perspective, then this is what it looks like. This is our pivot, which is at the point H, and this is our W, weight, or the center of gravity, which is the point G. Okay, and it is going to move clockwise if left to move along. He says the weight of the lamina force acts downward. We understand that. Explain why the lamina experiences a downward force. Now, it is experiencing a downward force because of the gravitational attraction. Simple as that. Gravity, gravitational attraction, or you can say the lamina is placed in the gravitational field of Earth. That's why it's experiencing a force downwards. Calculate the weight of the lamina on Earth. So simple formula, W equals to mg. And we are reminded again that mass has to be converted into kilograms. The mass is 50 grams, so this will be divided by 1000, multiplied by the value of g, which is 9.8. So when you solve this, your answer is going to be 0.49 Newton. So this is 0.49. Another approach to this on the in terms of calculator would be that since you're going to go from grams to kilograms, we know that dividing by 1000 is actually a prefix of 10 raised to the power minus 3. So this could have been 50 multiplied by 1 into 10 raised to the power minus 3 multiplied by 9.8, or simply put 50 into 10 raised to the power minus 3 into 9.8. This would have been a much quicker way of solving this. But if you are confused about that you can do this the long way or the longer way, which is this one. He says that the weight produces a moment, and the formula for moment we understand is F into D. Now please notice the units, it's Newton meters, which means the distances used in this equation will be converted into meters. So let's go back. Where is the pivot? This is the pivot, and this is the line of action of force. What's the perpendicular distance between them? Where is the perpendicular distance? This is the perpendicular distance. It has to make an angle of 90 degrees from both sides, from the pivot and from the component of force. Now we understand that the perpendicular distance making an angle of 90 degrees from both sides is actually 8 centimeters. So this is going to go something like this. So the force is easily found as 0.49, which is what we did at the previous part. The weight makes the force, and multiplied by distance, which is 8 centimeters, again divided by 100, because we need to make sure that the unit is going to be in meters. So this becomes, after calculation, 0.039 Newton meters. Write this answer over here. He says the laminar is now released from position 3.1. Describe what happens. So you have to describe, visually speaking, what's going to happen. So we discussed that this is going to be moving clockwise. So first, you will mention that it's going to move clockwise when it is released, right? So it moves clockwise movement, right? And what will you see? It will start oscillating, or it will be vibrating, or it will be moving left and right like a pendulum, right? What's going to happen at the end of the motion? When everything settles down, what's going to happen at the end? So it stops moving or stops oscillating, however you phrased it in English, stops moving when G is under H. When this all settles down, the value of G comes under the value, or the point G comes under the pivot H, is when this actually attains equilibrium and it will not oscillate anymore. So these are the 3 points you were supposed to make to get full credit for this part. Question number 4, as it appears from the face of it, is going to be from rho GH and barometer, I think, yeah. So we have a cross-section area, we have a density, right? We have the value of rho, tube is given, H is given, it's a dense liquid, base area is given, which is of course the cross-section area of the tube. So he says the atmospheric pressure is this much. Calculate the total pressure. Now, please be advised, whenever he says total pressure, that means that you're supposed to add the pressure of atmosphere with the pressure of liquid, which is rho GH. If it was pressure due to the liquid only, then we could have done rho GH only, and we would have gotten the full credit. Also look at the number of marks of this question, which means that something is missing or something you might overlook. So please be careful. Pressure at the bottom of the tube, right? Okay, so let's look at the bottom of the tube. You see, this is an open end, which means that the atmospheric pressure is acting on it. So not only this whole rho GH is acting at the base of the liquid, not only the liquid is acting as the pressure, but the atmospheric pressure is also being applied throughout the liquid due to Pascal's law. So the total pressure PT is going to be equal to the atmospheric pressure PA plus the pressure of liquid, which is PL. So this value is already given to us, which is 1 power 5. So 1 into 10 raised to power 5 plus rho GH, which is pressure of liquid. So density of the liquid is given in the question as 1.4 power 4. So 1.4 into 10 raised to power 4 into G, which is 9.8, into H, which is 1 meters of height of the liquid, given in the question. When you do this, the final answer is going to come out as 2.4 into 10 raised to power 5 pascals. So this will be 2.4 up to 2 significant figures, power 5. The force exerted on the inside surface of the tube, of the bottom of the tube. How much force is all of this causing at the base of the liquid? Now for the pressure, for the force to be found, we're going to go back to the formula for pressure, which is force over area. So we have pressure, we have the cross-section area, but we don't have the force. So pressure is what is being exerted. So this is 2.4 into 10 raised to power 5. Force we don't know, but the cross-section area is actually the same cross-section area that this bench has in contact with the surface of the liquid. Okay, so this will be 4 minus 4. So this is 4 into 10 raised to power minus 4. Make sure that this is in meter square. Yes, it is in meter square. Plus the part is for 2 marks, so no need to worry about conversion. So this is going to be F equals to both quantities being multiplied. The answer is going to be 96 newtons. So this managed to exert a force of 96 newtons in this process. Part B, he says a small glass, okay, open end of the tube. The tube is inserted in dense liquid. The open in the tube below the surface. Okay, fine. They're actually trying to make a barometer out of this. If you remember, this is actually how a barometer is made to find the atmospheric pressure. Now he says that the sheet of glass seal, this glass seal will be removed. It will be moved from this position and you can see that it is filled to the brim. It is fully filled. What happens is the tube is inverted. Okay, when you remove this lid, this liquid will start falling down because of its own weight, but it will stop at a certain point. It will not be able to fall any further. Why would that be? It will be primarily because of just one reason, and that is that, let's say that the liquid settles down at this point. It still wants to come out because of rho GH, because of the liquid pressure, but it is unable to do so. Why is it unable to do so? Because something from the outside is holding it back. Something from the outside is stopping it from coming out. And that something is actually the evidence of atmospheric pressure, because if there was no pressure on the outside, then this liquid still left in the tube can still escape into the container. Nobody is stopping it. Seemingly, nobody is holding it back. But we can see that something is, and that something was narrowed down to, you can say it was concluded that this is atmospheric pressure. Okay. All right, so he says, describe what happens. Again, a describing question. So please describe what you are going to see with your eyes in terms of science, in terms of scientific explanation. So what are we going to see as the sheet is removed? The liquid level falls. The liquid level falls, right? And after a while, it stops falling. The liquid level stops falling, right? And when is this going to happen? When atmospheric pressure is equal to the liquid pressure, right? All right. So based on this idea, he's going to carry the next question. I've drawn a diagram for this. Now, I understand this question is for 2 marks, okay? He says, describe an experiment and measurement to calculate the atmospheric pressure of the things that you've described. You see, the question is for 2 marks. I understand that you cannot draw an elaborate diagram, but if you have the time, if you think you have the time at the end of the question, then please do add this retort stand with a ruler and label the diagram with all the parts mentioned. And the most important part of the setup is that what height is supposed to be measured so that we can calculate the value of rho GH. We see the density of the liquid and the value of G is already known. What should be the value of H? Where should we measure it from? So we're supposed to highlight this with the help of a diagram, that it is going to be taken from the top of the liquid inside the tube to the top of the base of the liquid on the outside of the tub. And if you are unable to explain this in terms of words, that is why you need a diagram. Then you can label that this is the H that we're going to use in this formula of rho GH to calculate the value of atmospheric pressure. And of course, the ruler has to be held in place so that parallax errors can be avoided. And then you can accurately measure these 2 lengths or these 2 points to take the difference and then measure the value of H. All right. And you can go for the marking scheme for this description and memorize the answer. But I hope that we understand. Again, this is what is required. This is not required. But if you have the time, then please mention that the ruler is in place with help of a retort stand in terms of an ATP question as well. Question number 5 suggests that this question is from evaporation, as we can see in the title of the question as well. Okay. All right. So we can ready the vocabulary in our own heads that this is what he's going to be talking about. All right. So water drips. Okay, you can read the description. He says, when the water evaporates, the temperature of the water remaining sponge block decreases. It's becoming cooler because the temperature is decreasing. He's asking you the mechanism of evaporation, what you're going to write down. Movement of particles, why the decreased temperature occurs. So you have to talk about molecules and atoms. Okay. So you mentioned that the faster moving atoms escape the block, 1 mark. But when this happens, what does it do to the remaining particles that are present in the system still? Leaving behind, these particles are left behind, leaving behind particles, atoms, molecules, whatever word you've used, leaving behind particles with lowered kinetic energy. And we know that from kinetic model of matter, kinetic energy is directly linked to the temperature of the substance. That could be solid, liquid, and gas, right? Okay. Then he says, explain why energy is needed when the water is evaporating, or when the water evaporates. Why energy is required? Because water molecules are being held together in the structure in terms of bonds, right? That's why water becomes a liquid or stays a liquid at room temperature or below room temperature, because it has but it has bonds between its atoms. So in order for them to break free to become a gas as they evaporate, we need to break those bonds. And to break those bonds, we need energy, right? So what we can write down is that energy is needed for latent heat. And we understand that latent heat is the energy for the state of change, for the change of state. Energy is needed for latent heat to do what? To overcome the forces of attraction. To overcome the forces of attraction between the water molecules. Now it says state 2 ways in evaporation differs from boiling. How is it different? First, we don't see any boiling, and we can see that in boiling we see bubbles, but in evaporation we don't. That is a visual difference, right? Then evaporation can take place at any temperature. Boiling takes place at a specific temperature. Plus, the evaporation is dependent on the exposed surface area. If you increase the surface area, it increases the rate of evaporation. And of course, the temperature of the substance also controls or affects the rate of evaporation. If you have a hot liquid, let's say, at 70 degrees centigrade, and you have the same liquid in another container with all the physical formalities exactly the same way, but if it is at a lower temperature, then it is going to evaporate much slower than this one, right? So these factors affect evaporation, but they don't affect boiling. So you can mention any of the 2 points out of these 4 to support your answer. This question is from the chapter of sound. It says it produces a frequency of 800 hertz, right? We have a power supply, a loudspeaker. State what is meant by frequency. Now, this is a very specific definition. You're supposed to memorize this as it is. You can take the help from the marking scheme as well. So it says it's the number of wavelengths passing or produced, passing a point in what? In unit time, right? So memorize the definition as it is from the marking scheme. Explain whether the sound produced speaker is audible to the human and healthy hearing or not. You see, if you write down yes, that yes, it is healthy, it is audible, because we understand that the human range of frequency is 20 hertz to 20,000 hertz, then you're supposed to support this answer. Why did you say yes? You will mention that it is within audible range as the human hearing starts from 20 hertz and goes to 20,000 hertz, right? Describe the motion of the cone to produce the sound. Now we understand that the sound actually moves as compression and rarefaction, and then compression, rarefaction. To do this, what happens is that the cone has to move forward to produce a compression, and it has to move backward to produce a rarefaction. The same description goes in the answer as well, right? So you're going to write down that the coil or the cone moves, or you can say when the cone moves forward, what is produced? A compression is produced. When the cone moves back, what is produced? A rarefaction is produced, right? And this constantly changing regions of pressure produce sound. So these regions of changing pressures, of course, naming compression, refraction, produce a sound due to this cone, right? You can write this in your own words. The sun is a very large, extremely violent ball of gas, and electromagnetic radiation from the explosion of the sun reaches the earth. Okay, fine. Explain why sound. Now, again, this is a classic question, repeated question from the examiner, that we see that there are a lot of explosions happening on the sun, but why don't we get the sound on earth? Because if it reached earth, it would shatter the earth, quite frankly. But why is that so? Because sound needs medium to travel, and space has vacuum, or it has no medium. So sound cannot travel back to the earth. Question number 7 suggests that we have a fixed resistor and we need a thermistor. He says incomplete circuit is there, and he wants to connect a thermistor between T1 and T2. So very easy. So you please use a ruler for this diagram. Draw a thermistor. This is the symbol for the thermistor, which is a variable resistor that responds to the change in temperature. The next thing is The resistance of R is 2.5 ohms. The reading of the voltmeter is 0.4. What's the current in R? Now let's go back to the circuit. He says that the reading of the voltmeter is 0.4 volts, right? And the resistance of this resistor is 2.5 ohms. So how much current is actually passing through? You see, this is connected in series and the same current goes through the thermistor as well. So if I have the credentials of this resistor, I can very well find out the value of current by using Ohm's law, which is V equals to IR. So this goes 0.4 equals to 2.5 into current I. So I is going to be equal to 0.16 amperes, which is going to be written over here. The power transferred, again, we have P equals to IV, we have I square R, we have V square over R. You can use any one of these formulas and you're going to get the same answer. So the current is 0.16, the voltage is 0.4. This comes out as 0.064 watts. So this is 0.064. You can try this by I square R and V square over R. In terms of I square R, this will be 0.16 whole square into the resistance, which is 2.5. Or you can try V square, which is 0.4 whole square divided by 2.5. You will get the same answers. The temperature of the thermistor increases, and we remember that the resistance of thermistor is inversely proportional to temperature. He says that if the temperature is increased, let's say if the temperature is increased, it is being heated up, the resistance will decrease. That is one thing that we remember about this equipment. So he says, what will happen? Explain what happens to the reading of the voltmeter. Again, when he asked this question, it means what will you see with your eyes happening to the voltmeter? You see, we have predicted the first thing, that when you increase temperature, the resistance, please, you have to mention this, the resistance of the thermistor decreases. And since it is a series circuit, the voltage divides or is shared. The resistance of this fixed resistor, the resistance of this thermistor is falling. So its voltage consumption will also decrease, and a major chunk of this voltage or the supply is going to go back to the resistor itself, right? So if that voltage chunk is going to the fixed resistor, that means that the reading is being read by the voltmeter and the voltmeter reading is going to increase. Now, since it's a series circuit, major part of the voltage or more voltage will be left or show up for the fixed resistor. Hence, the voltmeter reading increases. Okay. All right, we move to question number 8. He says, we have a permanent magnet. State the name of the substance used to make and it's very straightforward. It's steel. The magnetic release move downwards and upwards. Okay, fine. The ammeter shows that the current in the solenoid. He says why there is a current in the solenoid. It's a classic question of Faraday's law. He just wants to understand, do you remember this or not? So in Faraday's law, we understand that if you provide a changing magnetic field to any conducting coil, it will produce induced EMF. If it produces induced EMF, if the circuit is complete, it will produce an induced current, and that current will be detected by the ammeter connected in series over here. So we just have to articulate all these points in a paragraph form, right? So what we're going to say, that magnetic field or magnetic flux is being cut or is changing for the coil. It experiences an induced EMF due to, mention the person who found this, due to Faraday's law, right? And in a closed circuit, induced EMF causes induced current, and hence we see a reading on the ammeter, right? Okay. But because if this was a voltmeter only, and if the ammeter was not connected, then we would have concluded our answer on induced EMF. There is a current in the circuit because there is an ammeter, right? Voltmeters have a very high resistance. They don't allow the flow of current. They just measure the voltage. The current causes the top end of the solenoid to become the south pole of the electromagnet. The bottom of the permanent magnet is the south pole. If that's the case, explain why the top end of the solenoid becomes the south pole if the magnet moves downward to the solenoid. So you see, the south pole is moving in, there will be a south pole over here. Where do we see this concept taking place before? We have seen this in Lenz's law. If you remember, Lenz's law suggested that whatever you're trying to do, the coil will do something opposite to nullify or to negate the effect that you're trying to produce. If you try to bring in the south pole, it will make a south pole so that it can repel you. If you try to take the magnet away, if you try to take the south pole away, it will make a north pole over here so that it can try to stop you from going away. But where is this north pole and south pole arriving or coming, or you can say it being caused in this coil? You see, the magnet moved, caused a flow of current in the coil. Now, using the right hand grip rule that we have for the fingers and the thumb, we figured out that the direction of current causes a pole on this coil. And that pole is in such a direction that it will always oppose whatever this magnet is trying to do. So in summary, in theory, we say that Lenz's law actually identified that how current opposes its maker. Whoever created the current is going to oppose the magnet that is trying to produce it. So one way or the other, we have to mention Lenz's law in this question. So what we can write down that according to Lenz's law, the induced current, be careful, the induced current in the loop causes such a pole on coil that it opposes its change, producing it, or opposes its maker. But the more technical way is to write it down this way, because we have picked up some bits and pieces from the definition of Lenz's law, and we've mentioned Lenz's law as well. So this will be the right answer for this. Part C suggests the magnet oscillates up and down. Describe what happens to the current solenoid. So very simple answer. As the magnet oscillates up and down, this oscillates to become south and north. It oscillates between them, which means that sometimes the current is clockwise, sometimes the current is anti-clockwise, right? So the direction of the current keeps changing. So direction of current changes. This is for 1 mark. And what happens to the magnitude? You see, when the magnet is moving at a very high rate of speed, slows down, stops, and then starts moving back up again. So the speed of the magnet is always changing. So at times it will be at a high rate of speed, at times it will be at a slow rate of speed, which means that the magnitude of the current is also changing. So you can mention that because we are observing this from the ammeter. So the current increases, then decreases, and keeps oscillating between a maximum value and a low value or a zero value, right? Question number 9. This is from space physics, I believe so. So yes, an interstellar cloud of dust of gases becomes a protostar. This is when it is trying to get birthed. This is when it is starting to form. Contains hydrogen. Okay, we know this. Describe the energy transfer that takes place when the cloud collapses and forms a protostar. So what happens when this takes place? So the gravitational potential energy of the imploding mass due to gravity is converted into thermal energy. Its temperature rises. When temperature rises, its kinetic energy rises, right? And when that happens, what can we say about the rest of this? Okay. And eventually, a protostar is being formed. Yes, because the star has not been formed. It is just colliding. It is just gathering the dust and cloud because of gravity. It hasn't become a star yet. Anyways, so the collapse result. Now this collapse results in the reaction of protostar, involves isotope of hydrogen-3. It decays by beta emission particle. State how the nuclei of isotopes, same element, are different. Is trying to ask you about the construction of the atoms. This is how the nuclei of isotopes have the same element are different. So they have same protons, but different neutrons. right? Very simple answer. Explain why hydrogen 3 cannot decay by alpha particle emission. So alpha is 4,2 and hydrogen 3,1 is 3,1. So if it had to decay to make this particle, then it needed to have at least 2 protons to do that. It cannot get rid of 2 protons because it already has 1 proton. It cannot make 1 proton out of the blue, right? So what are we supposed to say? We can say that alpha has 2 protons, 3H1 has only 1 proton, so not enough protons to release an alpha particle. Then we have an equation to balance. So this is 0 minus 1. We have this from memory. This is helium, which is going to be 3. And based on this is going to be 2. Okay. All right. So explain. Now this is the question. It says explain the nuclear reaction that in protostar stops further collapse as the protostar becomes a stable star. So this is actually the birth of a star. We have a memorized answer. We have a fixed answer. There's nothing new. So this nuclear reaction, that is this one that is being done at this point, the nuclear reaction produces very high temperature. So a nuclear reaction produces a lot of heat, or you can say produces a lot of internal energy. Due to this, we have some radiation pressure of, you can say, explosion outwards. This explosion, when balanced by or balances out by the inward gravity, by the inward gravitational pull, a stable star is formed. A stable star is formed. So for a star of this nature, the mass it has is so high that it is constantly pulling itself together because of gravitational attraction. But when it does so, as it is falling into itself, the temperature rises so much, it compresses so much that it is favorable condition for a nuclear reaction to take place. And as a result, it explodes or provides a lot of thermal energy to the system. So as simultaneously, the gases are falling into each other and simultaneously they are trying to explode outwards. So when there is a balance achieved between these two forces, between these two reactions, a stable star is formed. And this is what our sun is actually going through its life cycle right now. The cloud of dust as gas collapses into contains atoms of heaviest element. Now, heavy elements are only found when the star is out of its fuel, or it's running out of its fuel. It's close to its death. So state the part of the life cycle of the star responsible for producing heaviest elements. And this is when a supernova is being formed from a red giant. So from a red giant, when this converts into a supernova explosion or a supernova, these heavy elements exist in supernova, right? Red giant is when it runs out of hydrogen. This is the first stage it goes through. Okay. Question number 10 is from radioactivity, I believe so, yes. So it says isotope emits gamma radiation and one of the types of something else is being emitted. Okay, fine. So there is a magnetic field. This radiation is not being affected, which means that most likely this is going to be gamma radiation. It says mark the symbol gamma. Okay, sorry. So let's remove this and mark this with the symbol of gamma. Okay. He says, determine the other type of radiation. Now for this, you have to use the left-hand rule, right? So we have the magnetic field. So first finger will be pointing inwards because that is the direction of magnetic field. The second finger, or we can't see the second finger right now, but the thumb or the direction of force appears to be in this direction, which means that the force of the thumb or the thumb is actually will be open in the downward direction. This is your first finger. When you use your left hand in this situation, you will experience that the second finger opens up in this direction. This is your second finger. And we know that the second finger represents the direction of current. But is that the direction of current? No. Which means that this rule is actually for the positive charge. And if this is going opposite way, that means this is actually a beam of electrons. And what radiation is beam of electrons? That is a beta radiation. So the type of radiation is beta decay or beta radiation. Explanation, you will write this down exactly as it is over here, that the first finger using Fleming's left-hand rule is pointing inwards because the magnetic field is into the page. The second finger represents the direction of current, which has to be opposite. Please mention this opposite effect for the sake of beta radiation. And the direction of thumb represents the direction of movement of the charge or the force experienced by the charge. Okay, in another experiment, the beam of radiation from the sample is incident on a 5 mm thick sheet of lead. Now, lead stops everything. Okay, it stops alpha, it stops beta, it reduces gamma, but doesn't eliminate it completely. It's unable to do so. This is to state what happens to the two types of radiation. You see, beta is absorbed completely, it's gone. But the radiation level or the level of radiation of gamma is reduced. So gamma's intensity is reduced, but it is not completely absorbed. As I've discussed in the classroom many times, that lead sheets are used to reduce its intensity to safe levels or operational levels, but it's not possible to decrease it to a value of 0. You'll find this in A levels. There are numerous numericals that signify this idea that it is impossible to get it back to 0, but it's possible to get it down to a safe value. A very easy question. He says we have the frequency, we have the speed of light, what's the wavelength? So we use V equals to F lambda. This is 3 into 10 raised to power speed of light. F is 8.8 into 10 raised to power 19. Please make sure that you put in the right powers. Then we have the lambda. So lambda comes out as 3.4 into 10 raised to power minus 12, which is going to be written down over here.